So in this lesson, we will go over the transducer design in general and the purpose of backing material in particular in the ultrasound transducer. This is a very important concept, understanding of the backing material, because that results in or prevention of ringing of the crystals that leads to shorter spatial pulse length and eventually improved axial resolution. It is a little counterintuitive and complicated to understand, but using some analogies, I'll try to simplify it so that you can understand what the specific purpose of the backing material is in the ultrasound transducer. So let's consider the example of a bell in trying to understand the function of the backing material in the assembly of a transducer and its impact on axial resolution. As you will see in the subsequent example, when the bell clapper strikes the inside of the metal, there's one loud sound followed by continuous ringing or vibration of the structure of the bell that leads to generation of a single long note of sound that continues to vibrate even after the contact of the clapper with the metal of the bell is over. So this is referred to as continuous ringing, as you will see in the subsequent example. Now, let's contrast this example of a bell and a clapper with that of an alarm clock that keeps ringing early in the morning, and you're too lazy to get up and you just want to stop that alarm clock. Let's see what happens to that continuous ringing of the alarm clock when you put your hand on it and interrupt its continuous ringing and vibration. Now, if we were to compare these two situations, the first one with the bell's continuous ringing as a result of striking the clapper, we realize that one single long resonant frequency is produced as a result of this continuous vibration, as opposed to the alarm clock analogy, in which the ringing is interrupted by your hand by going over these two alarm bells on top of it. As you can imagine, and you can see that continuous ringing is converted into short clicks. So multiple frequencies are produced which are shorter clicks as opposed to one long resonant frequency. So now this has the most important implication for axial resolution, as we will see in the subsequent animation. So now let's try to apply these analogies to the transducer design and see how the application of backing material in the transducer results in damping of the continuous vibration of the crystals, leading to multiple short clicks with shorter pulse duration and therefore a better axial resolution. Backing material is one of the most important components of the ultrasound transducer, and in its assembly is applied in and around the piezoelectric crystals. The PZT crystals vibrate in response to stimulation. Now let's see what happens when there is vibration with or without significant backing. As you can see from the example, that there is a significant impact or damping on the pulse duration and the continuous vibration of the crystals. When there is low damping, analogous to the bell in the church, the result of clapper striking the bell, there's continuous ringing of crystals that leads to one long resonant frequency and a very long spatial pulse length. On the other hand, when the continuous ringing is interrupted by the backing material, multiple short clicks with a range of frequencies are produced which have very short spatial pulse length, which is important to improve axial resolution. Therefore, bottom line regarding the backing material is that it is applied in and around the piezoelectric crystals to prevent them from continuously ringing as a result of stimulation. That interruption of ringing by the backing material results in production of multiple short clicks as opposed to one long resonant frequency. These short clicks have a range of frequencies in them and leads to shorter spatial pulse length, which eventually leads to an improved axial resolution. So that's the function of the backing material, that it causes damping to shorten the spatial pulse length.